Okay, I'm already regretting doing this, but let's explain more things. Today we'll be talking about the FAT system versus the ext2 system. So let's start with FAT. What is FAT? If you've worked with disk drives before, you've probably heard of, FAT32. FAT32 is a really common file system, but we'll be focusing on FAT. FAT stands for File Allocation Table. So the file allocation table is the key defining feature of a FAT file system. And today we'll be talking about what problems it solves and other approaches, which is like the ext2 file system, which is similar to the ext4 file system you may have heard of if you've used any modern Linux distro. Okay, let's start. So let's start with abstraction. You have your hard disk drive. You normally think of it, oh, spinning disk, oh, there's a platter, very funny. It's very old style disk. But within each disk, there is different, we call them different sectors. Different sectors are like different parts of the disk that store data. And within each sector, there is a list of blocks. So blocks are just the smallest unit of data that you can write. In some cases, it could be like 512 bytes. Some cases, it could be more, it could be less. But let's just say one block is the smallest unit of allocation. So we want to allocate these blocks to files. I have files, it look like this. You can say, oh, it's a PDF file. I want to store this PDF file in these blocks. So how do I allocate the files to a block? Of course, we will need some sort of mapping. So the simplest idea is, okay, let's label these blocks 0, 1, 2, 3, 4, and 4 and 5. And then I have a table that says, okay, this has a.pdf, this is the name, and then goes to the block number, which is, let's say, 2. And so I can know that, hey, this file is actually here. That comes the first question. That's only if you want to store a singular file that's less than the block size. Of course, our files are a lot larger than 512 bytes now, so how are we gonna do that? Well, if you've ever taken any data structures course, you would know that the solution is quite obvious. It's called linked list. A linked list is how you can link different blocks of data together. Perfect for this example, since we're literally using blocks. So let's say block 2, I expand it to be like this. So and this is the block inside, it's 512 bytes. First part could be, oh, here's the actual data, and now here you have a pointer. You have a pointer to the next block of the data. So let's say pointer points to number 4, and so this points here, and so now I cannot draw on this. Yeah, so let's say this points say this points here. So okay, so now 2 points here, which points to 4, and now I can repeat this process until I get an arbitrary large file. So this solves this file size issue. Now the last part of the issue comes in, let's say I have a PDF file, let's say it's 1,000 pages long, and I want to scroll to the 500th page. Now, it would be unfortunate if we had to go through all 500 pages. It's like a scroll bar. You have to scroll so far just to get to the middle. So what if we could just jump to the middle of the file? With this linked list method, you can easily see that it is impossible to see where the next files are without actually going through all of the different blocks. So I could start with 2, and I have to go through 2, then 4, then 5, and so on, just to find the middle of the file. And so how is there any way for us to tell where this file is, where the things are? Is there a way to see where the jumps are going to go so that we can follow them? Short answer is not quickly. If we want to use a linked list, it comes with this drawback that you have to iterate through it sequentially. However, how we do it is very important. Right now, we are storing all these information about the jumps, about the links, about the pointers within the block itself, and the block is on your hard drive, and hard drives are slow. Of course, we have something a lot faster. We call it memory. So it's your RAM chip. It's your RAM chip. I cannot draw, but this is your RAM chip, and it is fast. And we have a bit of it. Let's say like 8 gigs on like any decent system nowadays. And this is enough to store some basic bookkeeping information. So what if we move this list into memory? So if you can go iterate through memory much orders of magnitude quicker than your hard drive, then you can jump through it a lot faster and find the 500 page instead of slowly fetching all 500 blocks from the hard drive. And that's exactly what we do in a file allocation table. So file allocation table is actually the file allocation itself. The file allocation table itself isn't just a linked list. It stores a lot more extra things. So what actually happens is for each block within the file system, we have an entry in the file allocation table. And in each of these, we store the state of the block. So let's say block 0 is empty. We would mark it as free. Let's just call it F. Block 1 is empty. We call it F. But block 2, normally we link block 2 to block 4 within the block. But in this file allocation table, we can just say, oh, 2 is supposed to be linked to 4, 4 is supposed to be linked to 5, and I say 5, let's say there's nothing left. 5 can be an end of file, EOF. That means after this, we do not try to iterate to anything else. Now, the beauty of this is, let's say I have another file, let's say I have b.jpg, and I want this to be stored in file number 3, that's here. So I can just put EOF here. Let's say the file fits within the block. I can store information about this new file in the existing file allocation table without having to make any changes, because how you read the value depends on what brought you there. That's a bit abstract, so let's say I'm looking for a.pdf. I can look within this table and I can say, oh, 2 jumps to 4 jumps to 5 jumps to end of file. But if I'm looking for b.jpg, I just start from 3 and I say, oh, that's the file, that's where it ends. So it's a very elegant solution to store this information about the linked list. So this is the file allocation table approach, and it's so successful it's used in most systems, including embedded digicams, the oldest systems, the newest systems. So if you have a USB drive formatted as a FAT, it can probably work anywhere across Linux, Mac, iOS, even iOS, yeah, Mac OS, everything. It will just work. That's how widespread and simple FAT is. However, there's always an alternate approach, which in this case we are going to discuss EXT. So EXT stands for Extended File System, and we are currently talking about EXT2. There is EXT4, but we won't talk about that today. So what the extended file system brings is another concept. It doesn't use this linked list to store the information. So listen up instead how this works. Within a partition of EXT, within EXT2 partition, there are multiple things called block groups. We call them BG0, 1, 2, 3. So block groups are, you guessed it, groups of blocks, and they're grouped together for multiple reasons, which I'll say later. But within each block, there is a lot more structure. There's this thing called a super block that stores information about the entire disk. It's repeated across every single block. That's how important the data is. It's for redundancy. And then there is the block info, which stores information about blocks across the entire partition. So, what is how many free blocks are there? How many free inodes, which I'll talk about later, are there? How many free blocks are there? So everything is stored within this block info, and this only stores very bare level info. It's just like, 500 out of 640 are free. It doesn't tell you which is free, it just tells you how much is free. So it's very general statistics, and hence we're able to duplicate this across every single block group as well. Now we get to the block specific information. So we have two chunks of space allocated here for two bitmaps. A bitmap just checks whether something is 0 or 1. We normally use it to check if something is free or not free. So in this case, we have a block bitmap to check if blocks are free or not, which is here. These are, okay, I'll just note this out first. inode block. So the block bitmap checks if the bitmaps are free to use. So it checks which blocks are free. And we have a inode bitmap, which, surprise, checks if the inodes are free to use. So basically, this is how we keep track of whether something is free or not. Here we had the free elements. We had a free one here to check whether they're free or not. But now we use a bitmap. So a bitmap brings a benefit over a linked list because a bitmap is a lot more efficient. It's just checking for zeros and ones. While for a linked list, you have to go through the list one by one. Although to be fair, over here it's also a sequential array. I won't talk about that. Let's not talk about that. I have no time left. So let's talk about inodes. Inodes are called index nodes, and they store information about each file. So each file has its own inode. And this inode stores information like the name, access times, permissions, etc. But the cool thing is, it stores different levels of pointers to blocks. So let's say these are different pointers. These are pointers to blocks that store the information for the file. And these last three blocks have special meanings. They are the single indirect, double indirect, and triple indirect pointers. What they mean is it's something like paging. So if you have to say this is the single indirect block, it will point to another block that stores all pointers. So these are all pointers that can point to other blocks. So think about how much more space that unlocks. Instead of having limited to these amount of pointers, you can use all of these pointers. And double and triple indirect blocks do this even better. So you point to one that's pointing to pointers, and each of these pointers point to another block that is full of pointers, and now each of these then point to the blocks. So think of how much space this gives. In fact, in theory, you can extend this more and it can become infinite, but in ext we limit it to single, double, and triple indirect. But that's more than enough, and that's a lot more files. That's a lot bigger than you actually need in real life. So this allows for a lot of flexibility in file sizes. And so yeah, that's about it for how differences between FAT32 and ext2 work. Yeah, I hope that was a clear explanation.